everyone. Our new chapter, gravitation. Previously we were introducing, there are two chapters. Now first one, motion in a straight line. Now second one, motion in a plane. We are introducing our motion in a plane in there are similar quantities. Now first two quantities, displacement, velocity and acceleration. Today we are discussing about the main equipment and main relations of acceleration problem. Okay, now we are going to the chapter name, gravitation. Very important one, 4 marks. Okay, gravitation. 4 marks. Okay, no gravitation. Now what is the definition of gravitation? Clearly we observe one. Now what is the definition of gravitation? Right, we are going to the statement of definition of gravitation. Clearly, now, before we are going to the definition part, what is the examples of gravitation? Clearly, we observe one. Okay. Now, there are some of real-time examples in our time period. Clearly, when a ball dropped from a top of the building, when a ball dropped from a top of the building, okay, dropped from the top of the building. Okay, ball dropped from the top of the building. Now next one we can take as same similar one we can take into drop objects. Okay. Now third one, the last one example we can take as rain falling. Which one? Rain falling. These three examples we can take as in gravitation one. Clearly you know that when gravitation means we can take in when an object dropped from the top of the building. Now second one we can take as the same way we can take in using our objects. Objects should drop from the earth surface. The last one rain falling. Clearly you know that rain falling is the nature one we can take in. Right? This is the example. Now what is the definition of gravitation? Clearly, now what is the definition of gravitation? Now what we can take as gravitation? The force. Clearly, the force which is exerted by the surface of the force which is exerted by the surface of the earth. Clearly, now exerted means we can take it as when a ball dropped from a sum of statement in universe we can take it. Clearly, in the universe we can take it if any object dropped from top of the height. Clearly, now which is exerted by the surface of the earth we can take it. The surface we can always when a ball dropped from the earth surface. Now this is the gravitation one. Clearly, now gravitation we can take it drop from the top of the building, drop from a ball, top of the building, drop object, okay, drop from object and rain falling. These three examples we can take in gravitation. Clearly. Now next one. Now gravitation we can take in the some more one. Introducing scientist Newton. Clearly you know the scientist Newton. In your 8th standard physics textbook, in science textbook we can take in Newton. Clearly, Newton's law of gravitation, we can say with example in this here. Now, what is the Newton's law? Newton's law we can take in when an object dropped from a top of the height we can take in. Clearly, in Newton's laws we can take in as he is in tree. Clearly, okay, sitting on tree or sleeping on tree we can take when an object, when an apple dropped from his in top of the bottom. Clearly, is that we can take in as Newton. Okay, Newton's law of gravitation. Newton's law of gravitation. This is the Newton fundamental we can take it. When a tree we can using observe when an apple dropped from a earth surface we can take it as we can using in Newton we can observe these fundamental we can take in Newton's law of gravitation. When we use the gravitation fundamental we can use the topic in Newton's law of gravitation. Clearly, now this is the gravitation fundamental. Now next one, universal law of gravitation. Now what is the universal law of gravitation? Clearly, what is the definition of universal law of gravitation? Now, what is the constant filament of Newton's law of gravitation? Clearly, now gravitation we can introduce in the symbol of capital G. Which symbol we can take in? Capital G. Now, what is the constant number we can take in? 6.67 into 10 to the power of minus 11. This is the constant number. Figure we can approach it in. Figure we can approach it in. The units also fundamentals we can take it in universal law of gravitation. Okay, now next one. Universal law of gravitation. Now, what is the definition of universal law of gravitation? For example, we are choosing in every surface in universe when two objects are attracted. Okay, in universe, if any two objects are attracted each other. Clearly, in universe, if any two objects are attracted each other, for example, we are using any two objects, the first object A and second object B, which is always attracted. For example, we are choosing this is the object which is attracted to Earth's surface. This is the first object, second one is the second object. Now, first object you can take in, this is the marker one, this is the object. Now, second object, Earth one. When I drop from this the height of, clearly, which is attracted to the Earth's surface. This fundamental you can take in as universal law of gravitation. Clearly, in universe, if any two objects are attracted each other. Clearly. Now, next one. Next one. The force is always, okay, this is the first mass m1, this is the second mass m2. First mass m1 and second mass m2. The force is always directly proportional to, okay, their masses. You can take it as m1 and m2. There are two masses. Okay, and inversely proportional to. Okay, this is the distance between any two positions. This distance we can take it as small r. Okay, and inversely proportional to square of distance. Square of distance. And you can take in a bracket r square. Clearly, in universe, if any two objects are always attracted each other. Okay. Now first we can take the first object A and second object B. The first object mass of the body m1, second object mass of the body m2. The distance between any two objects you can take in as r. Clearly, the distance between any two positions, the first position of object to second position of object. This is the distance between A and B, you can take in as r. Okay, clear? The force is always directly proportional to their masses m1 and m2, and inversely proportional to square of distance you can take in r square. This is the universal law of gravitation. Okay. Now next one we can take it as universal law of gravitation in mathematical explanation. Which explanation? Mathematical explanation. Mathematical explanation. Now, what is the mathematical explanation? Now, explanation means we can take it as equation of universal law of gravitation. Equation of universal law of gravitation. Mathematical expression. Okay. Now this universal law of gravitation, which is denoted by, we can take it as denoted by capital G, which we can take it capital G is the universal law of gravitation. Okay. Now mathematical expression we can take it. For example, if any two objects, the first object A again second object we can take it B is the second object. Now first object mass of the body we can take in small m1, second object of mass of the body m1 and m2. Okay. Now distance between any two objects. Okay. Now first object to second object we can take in as, this is the distance we can take in as small. Okay. The expression we can take in as the definition of the universal law of gravitation or statement of universal law of gravitation. Clearly, in surface, in the universe, if any two objects are attracted each other. Clear? Now first point. Now second point we can take it. The force is always directly proportional to their masses, two different types of masses. Now first mass m1 and second mass m2. The force is always directly proportional to m1 and m2. There are two masses. Okay? And inversely proportional to square of distance. Now F is inversely proportional to r square. These two fundamentals we can take in as in our statement. The force is always directly proportional to m1 and m2. The force is always inversely proportional to square of distance. Clearly? Now the mutual of these equation we can take in as equation 1 and equation 2. Okay? From equation 1 and 2, first equation and second equation. Right? There are mutual equations you can take it. F is directly proportional to m1 m2 by r square. Clear? F is directly proportional to m1 m2 by r square. Now proportionality we can negligible, that the constant we can applicable. The constant F is equals to capital G is the constant one. m1 m2 by r square. This is the universal law of gravitation in force equation. F is equals to capital G into m1 m2 by r square. Okay. Now what is capital G? Capital G means universal law of gravitation constant. Universal law of gravitational constant. Clearly? Now what is the fundamental value of capital G? Now what is the constant value of capital G? Since capital G is equals to 6.67 into 10 to the power of minus 11 Newton meter square per kg square. This is the constant number. Now what we can gain of units? Units we can applicable in our next topic. Now G is equals to 6.67 into 10 to the power of minus 11 Newton meter square kg square. Now this is the universal law of gravitation of mathematical expression. Okay, clearly? Which is denoted by capital G. Capital G means we can take it as universal law of gravitation constant. Okay? If we can take it as any two objects, first object A and second object B. First object mass of the body m1 and second object mass of the body m2. The distance between A to B we can take it as r. R means distance position. Now F is a fundamental we can take it as our statement. The force is always directly proportional to their masses m1 and m2. Okay? The force is always inversely proportional to square of distance. Now F is directly proportional to 1 by r square or F is inversely proportional to r square. Okay? Now from equation 1 and 2, F is directly proportional to mutual one m1 m2 by r square. Now F is equals to proportionality is always negligible factor. Now what is the constant factor we can take it as universal law of gravitation constant capital G into m1 m2 by r square. Now G means we can take in universal law of gravitation constant. So capital G is equals to 6.67 into 10 to the power of minus 11 Newton meter square kg square. Okay. Now next one, units of universal law of gravitation. Okay. Now this is the constant. Now what is the units we can take in? How we can apply in Newton meter square kg square? Right? We can go into units of capital G. Units of capital G. Okay. Now what is the equation of universal law of gravitation? in mathematical expression, F is equals to capital G into M1 M2 by R square. M1 M2 by R square. M is the mass of the body, M1 and M2. R is the distance between any two objects. Now distance of objects, A object and B object. G is the constant one, universal of one constant. Now what is the G value? 6.67 into 10 to the power of minus 11. Okay. Now next one. Units of capital T. Units of capital G. Now we are going to our equation. F is equals to capital G M1 M2 by R square. This is the first equation. Units of capital G. Capital G is the constant one we can take, right? Okay. Now R square is the denominator function. F into R square is equals to capital G M1 M2. Now M1 M2 is our multiplication, which is completed to the next expression. F into R square by M1 M2 is equals to capital. Now equation capital G is equals to F R square by M1 M2. Now this is the universal of gravitation. Capital G is equals to F into R square by M1 into M. M1 into M. Clear? Since we can take an units of F, force units we can take as an SI units, newtons. R is the distance. Distance units we can take in meters. Mass of the body, kg. Again we are choosing mass of the body, kg also. Right? Capital G is equals to force we can take in units N. R square. R square means we can take in meters. Meter square. By M1 and M2. M1 we can take in kg. This one also kg. Kg into kg. Capital G is equals to Newton meter square by kg square. Or same units we can apply to capital G is equals to Newton meter square kg to the power minus 2. There are two SI units of capital G. Capital G is always universal of constant. This is always constant, which can be applicable in always universal constant. Capital G is equals to, now what is that number? 6.67 into 10 to the power of minus 11 Newton meter square kg to the power minus 2. This is always constant in universe. In universe. Clearly, this is the units of capital G. Now F is equals to capital G into M1 into the R square. Now Fr square is equals to capital G into M1 into. Now Fr square by M1 into is equals to capital G. Now G is equals to Newton meter square kg square. Newton meter square kg to the power minus 2. Now this is the units of capital. Now next one. Cavendish method. Which method? Cavendish method. So what is Cavendish method? Okay. Now what is Cavendish method? In Cavendish method we can take it as universal of gravitation constant capital. There are representative function. Now what kind of representative function we can applicable? The representative function we can take as any two different types of masses applicable to again to their masses. The short masses to higher masses also. Okay, now next one. Cavendish method. Cavendish. So what is Cavendish method? In every expression we can take it as in which one? Label expression. Now what kind of label we can take in Cavendish method? For example, I choose the rigid support. Which support? Rigid support. Okay. This is the center of the point. Okay. Then a string. I am using the string. Okay. Now this is the I am using the plank also. tie there two balls. Tie there two balls. Okay, M1 and the M2 balls. Here, this is the rigid support. We tie to string with the plank. Okay, with the plank tied to bars also. Again, I am choosing to the again one. Higher masses. You can take one higher masses. Now, first again I am choosing to these points we can take in. Okay. The first using the rigid support tied to string. Okay. Again I am choosing to the plank, wooden plank we can take in. Okay. There are two masses of edge of the masses. The first mass of the body and second mass of the body. This one is M1. Again you can choose it M2. Again also you can take it that the M1 mass of the body, M2 mass of the body. Okay. I will apply some force, external force are applicable. The force you can applicable to these plank you can take in this one, rotate it. Which one you can rotate it? The first rotating to the second rotating. This is the rotating one. Okay. Now these down balls rotating to their sufficient positions at the same time. This string is twisted. String twisted. Twisted one to any two balls also. When the down section balls we can applicable in rotating to their positions, their constant positions. The string, the positions will be rotated, the string also twisted. Again, these two balls are also rotating to their parallel positions. Their parallel position rotating to these positions. Now these positions we can take it as in this twisted one. Which one we can take it? Twisted one. Okay, twisted one. Okay, where applicable twisted force is equals to the every force we can applicable to in our gravitation purpose of their masses we can applicable in universal law of gravitation. Which one we can take it? Universal law of gravitation. Now what kind of universal law of gravitation? Now these gravitation that we can applicable to these positions. Okay. Any two balls are rotated to twisting of the twisted of this string. Again, those balls also rotating to constant positions also. Okay. Downward we can take into the downward rotating the same. We are not rotating to the upward of balls. We are rotating only for downward of the balls. The string also twisted. Again, balls are rotating to these kind of rotation. Again, first position to second position to third position. The position will be changes to at first universal point to second point of this position. Clearly, now this one twisting force. Twisting force is equals to universal law of gravity. Universal law of gravitation. Universal law of gravitation. Now what is twisting force? The twisting force you can take it as torque tau. And tau is equals to, now what is the equation? The force F is equals to, you can take it as, okay, if you can take in the force universal law of gravitation. Torque tau is equals to force F. Now torque tau is equals to F means we can take in capital G M1 M2 by R square. Clearly, torque tau is equals to capital G into M1 M2 by R square. Now torque we can take in as applicable in this surface, the rotating to universal surface. The universal surface we can applicable angular force. Which force we can take in? Angular force. Now what kind of angular force? Clearly, now torque tau is equals to L into theta. L means we can take in as, now what kind of we can take in? L is the angular momentum, theta is angular displacement. The momentum will be applicable to at zero saturation position to the infinity of saturation positions in our surface. The rotating to the circumference of the surface we can take in. L means we can take in as which one? Angular momentum. Theta means angular displacement. The displacement we can take in as the rotating to the circumference of the surface we can take in. The circle of the surface we can take in. These kind of imaginary part we can take in as twisting force torque tau is equals to L into theta is equals to, we can take in capital G M1 M2 by R square. m1 m2 by r square. Now this is the Cavendish method. Clearly, in Cavendish method we can applicable twisting force applicable. Again we are using the force also applicable. Clearly, now this one also force. Again this one also force we can take. The force is a normal force we can take. Now this one is angular force we can take. Angular force is applicable when object travels to circumference of these positions. We can take the constant one of the circumference of these positions. We can applicable. Now torque is equals to force F. Now torque is equals to capital G into m1 m2 by r square. Now L into theta is equals to capital G into m1 m2 by r square. Now this is the Cavendish method. Now clear? Now next one, acceleration due to gravity. Now next one, acceleration due to gravity. Now what is the acceleration due to gravity? Now where we are using? Now what is the constant element of acceleration due to gravity? Acceleration due to gravity. Acceleration due to gravity. Now what is acceleration due to gravity? Now what kind of information we can take? Which is indicated by, we can take as a statement, we can take an applicable acceleration due to gravity. In according to universal law of gravitation, we can take as in every body freely falling. In every body freely falling. For example, I choose this one is an object. It one can take as freely falling body. This is a downwards freely falling body. When an object travels from due to the earth, we can take it. When a body projected one height of the building and drop from top of the building also. Take ground to the statement. We can take it as when an object freely falling. When an object freely falling. When an object position A to position B. The position A is when a ball dropped from the height of this building, dropped to the earth surface. Okay, earth surface. You can take it as in universal law of gravitation, every object freely falling due to earth surface. Due to earth surface. When a ball dropped from a top of a building or freely falling body due to the earth surface. Okay, due to the earth surface or surface of the earth also we can take it. Due to the surface of the earth we can take it. And also right. Surface of the earth. Now this is the acceleration due to gravity, which is denoted by small g. Okay, small g we can take it. Small g in our ground falling to, we can take it as the small g value. We can take it. G is equals to 9.8 meter per second square in small g value, which is changes the positions also we can take it in surface, in ground states, in upper state. Clearly, there are three positions we can take as upper state. We can take when an object travels from top of the statements. For example, choosing when an object starts from ground to the projected one. When a ball projected to top of the building, we can take as the acceleration due to gravity. A is equals to negative side, projected one. A downward state at A is equals to positive one. Clearly, the statements we are applicable to, then the positions will be changes in the situations of small g also. Clearly, now downward direction we can take it as A is equals to positive g, downward direction. At upward we can take it as A is equals to negative sign. Since we can take it, the positions will be average of small g is equals to 9.8 meter per second square. Their positions will be changes in ground or upward or downwards. Clearly, this is the acceleration due to gravity statement. Now next one we can applicable what is the mathematical expression. Okay. mathematical expression of gravity. Mathematical expression of gravity. For example, we can take it as the force F is equals to, we know that our previous one, universal law of gravitation one. Okay, the force capital F is equals to, there are two positions of this here. Now we can take the first position and second position also. We can take an object of, for example, this is the surface, earth surface. We can take it. Which one? Now this one is earth surface. Now this is the center of the point. Clearly, earth surface and center of the point. Now this is the radius of this position. R. Which one we can take? An earth surface. Now mass of the body M E. Clearly, if there are two using to the mass, only we can take as the earth surface. In earth surface, we can take when an object center position to the edge of the surface, edge of the circumference we have taken. R E, E means earth radius. Okay, E means earth of mass earth. Clearly, we can take now force F is equals to, actually we can take capital G, capital M, small m by R E square. Capital M means we can take it as earth surface, M is the mass of the body. Again, we can choosing mass of the body. R E means we can take it as the earth radius square. Clearly, since we can take capital F is equals to our your 9th standard, 8th standard, you can take it from Newton's second law. Newton's second law. F is equals to M. F is equals to M. Since we can take it, now F is equals to MA is equals to capital G, capital M E M by R E square. Okay. Since we can take A means acceleration due to gravity, G downward direction we can take. Okay. Now mg is equals to capital G, capital M E M by R E square. Small m get cancelled. Now we can take G is equals to capital G, capital M E by R E square. Now this is the acceleration due to gravity expression. We can take it clearly. Now acceleration due to gravity, when we can take it as, there are two positions we can apply in our real surface. Okay, now first position we can take it when a ball dropped from a height of perspective, dropped from a free fall. Clearly, now downward we can take it as A is equals to positive 1. When a ball thrown upward direction, now upward direction when a ball object direction, height of the direction. Now A is equals to minus. We can take it, this is the average value we can take it in the ground state 9, G is equals to 9.8 meter per second square. Clearly, every object in free fall we can take it due to surface of the earth we can take it. In every body which is attracted to the surface of this position we can take it. Which position? Surface of the earth, which is denoted by small g. In our mathematical expression, for example, we are choosing to, now this is the earth surface, the total we can take it as earth surface. Okay, now this is the mass of the earth ME and radius of earth RE. Okay, now F is equals to, we can take in our previous equation, F is equals to capital G M1 M2 by R square. Now M1 means M, M2 means we can take it as capital M E. E means earth surface. Now this one is R E square. Now from Newton's second law we can take it F is equals to MA. Now MA is equals to capital G, capital ME M by R E square. MM get cancelled, we can take it. Now remaining equation, small g is equals to capital G into ME by R E square. Now this is the acceleration due to gravity. Clear?